Hello everyone. Today, I would like to share my research titled Implementation and Performance Evaluation of a Vision Transformer Model Based on an MCU with an NPU. This paper has been submitted to KICS Winter Conference 2026. In this presentation, I will talk about how I redesigned a vision transformer model so that it can run on a very resource-limited microcontroller that has a built-in neural processing unit, especially STM32N6. I've released the code on GitHub. The table of contents is as follows. Recently, the number of IoT and edge devices has increased rapidly. Because of that, running AI directly on these devices without relying on the cloud has become very important. Running AI on the device has a few clear benefits. It reduces latency, since the data does not need to travel to a server. It improves privacy, because the data stays inside the device. And it also makes the system more stable, even without internet access. Especially, MCU is a low-power processor integrating the CPU, memory, and I/O ports onto a single chip, and therefore it is optimized for resource-constrained systems. However, there is a big challenge. Most microcontrollers have limited processing power and memory. On the other hand, modern AI models, especially transformer-based models, require a lot of computation. Because of this mismatch, it is not easy to run such models directly on MCUs. To address these limitations, some modern microcontrollers now include a neural processing unit. The NPU helps accelerate deep learning operations. But running transformer models on NPUs, embedded in MCUs, is still uncommon. It is because most NPUs embedded in MCUs are originally optimized for convolution-based models, not transformers. So in this work, the main goal is to redesign a vision transformer so it can run efficiently on such hardware. In this research, I used the STM32N6 microcontroller, which includes the ST Neural Art Accelerator, a specialized NPU. This NPU is optimized for quantized neural networks, especially CNNs, but it does not support every operation. Unsupported operations automatically fall back to the CPU, which slows the model down. Moreover, some operators cannot be executed on CPU because the NPU compiler fails to compile. So the model must be designed only with operations that the NPU can accelerate or NPU compiler can compile. The comparison table in the slide shows that the NPU-based MCU performs much faster and uses less energy compared to a CPU-only MCU. This clearly shows the importance of using an NPU for on-device AI. Next, let me move on to the redesign of the vision transformer. The standard vision transformer includes a patch embedding layer. However, if the model includes both patch embedding and self-attention, the tool used for model analysis, called ST-Edge AI, cannot process it. To solve this, I removed the patch embedding module from the model and instead performed patch embedding during pre-processing before feeding data into the model. This makes the model compatible with the compiler. The next modification involves the activation function. The original vision transformer uses GELU, but the NPU does not support GELU in its TensorFlow Lite implementation. Because of that, I replaced GELU with ReLU. ReLU is supported by the NPU and can be executed efficiently. Although this change may slightly affect accuracy, it greatly improves compatibility with NPU and NPU compiler. Another adjustment involves the fully connected layers. The NPU supports only fully connected layers that take two-dimensional inputs. However, the fully connected layers in the original vision transformer have three-dimensional inputs. So during compilation, NPU compiler removed the existing batch axis from the input of 3D fully connected layer. In detail, it removed the original batch axis from the input, one patch, dim, and set the patch as the batch axis, resulting in input of the form patch, dim. However, broadcasting bias at the batch axis is not supported by the NPU and NPU compiler. I think NPU compiler expected the batch size is 1, so I removed the bias from these fully connected layers. This allows the NPU to process the operations without encountering error. In some cases, I still wanted to keep bias in the model. To do that, I replaced the fully connected layers with 1x1 convolution layers, which behave similarly and can include bias. These 1x1 convolution layers are fully supported by the NPU, so this was a good alternative. Because of this, I created two versions of the model, a version without bias using fully connected layers, and a version with bias using 1x1 convolution layers. This allowed me to compare performance differences caused by these design choices. Since the NPU supports only 8-bit integer quantized weights and 8-bit unsigned integer inputs, I applied post-training quantization using TensorFlow Lite. In this setup, the weights are converted to 8-bit integer, the inputs become 8-bit unsigned integer, and the outputs remain in 32-bit floating point. Once the model is modified and quantized, it needs to be compiled using STEdge-AI. The compilation process converts the model to an ONN structure file and a JSON weight file. During compilation, the tool assigns different operations either to the CPU or the NPU. The output of the compilation is 3 files. One file describing the model structure, one file storing the weights, and one file that contains NPU-specific instructions. In this mapping, fully connected layers and one-by-one convolution layers are executed on the NPU, but the matrix multiplication operations inside the self-attention module are assigned to the CPU. This becomes important later when we examine performance. This figure shows the CPU and NPU allocation details for operators used in the vision transformer model. The patch embedding is performed in pre-processing stage. Operators marked in orange run on the NPU, while those marked in light green run on the CPU. Models incorporating bias parameters replace all fully connected layers except the one used for classification with one-by-one convolutions containing bias parameters. To evaluate performance, I prepared 4 different vision transformer models: tiny, small, base, and large. Each model has different image sizes, hidden sizes, numbers of layers, and number of attention heads. I also compared versions with and without bias. The table summarizes the detailed model specifications such as the number of parameters and the number of multiply-accumulate operations. For evaluation, I used 2 development boards. The first one is the STM32N6 DK board, which has both a CPU and an NPU. The second one is the Nucleo 753ZI board, which has only a CPU and no NPU. This makes it useful for comparison. The models were trained on a PC using a dataset of 5 categories of fresh flowers. This dataset was originally used in a flower recognition challenge. Now let me present the results. First, regarding inference speed, the NPU provides a huge advantage. Across all model sizes, the STM32N6 achieves an average of about 91% reduction in inference time compared to the CPU-only MCU. For example, the tiny vision transformer model takes around 12 milliseconds on the STM32N6, while the same model on the Nucleo 753ZI takes over 100 milliseconds. Second, models with bias, which use one-by-one convolutions, are slightly faster because those operations are more efficiently handled by the NPU. Third, self-attention becomes a bottleneck because it still runs on the CPU. As the number of patches increases, the cost of self-attention increases quadratically. This means larger vision transformer models show bigger slowdowns, even when the NPU accelerates the other parts. This demonstrates that NPU can further reduce inference time when supporting self-attention. Finally, there are memory limitations. The largest model, Vision Transformer Large, uses more than 1 megabyte of memory and therefore cannot run on the STM32A7 due to memory constraints. However, it can run on the STM32N6 because it has much more available memory. This slide shows a demonstration of the model running on the STM32N6 board. The model predicts the flower category correctly and shows the inference time on the display. This confirms that real-time inference is possible for smaller vision transformer models on this hardware. In this research, I redesigned a vision transformer model so that it can run efficiently on a microcontroller equipped with an NPU. I modified several parts of the architecture. In the experiments, the NPU-based MCU showed around 91% faster inference compared to a CPU-only MCU. This demonstrates that transformer-based models can be deployed on low-power embedded devices with the help of an NPU. For future work, I plan to test these models on newer MCUs, like the Aleph Ensemble E8, which includes an NPU that can accelerate self-attention. This will allow us to evaluate the real-time ability of vision transformer models more accurately. References are on-device model survey paper, vision transformer paper, and many STM32N6 and STEdge-AI documentation and forum. In the appendix, we will look at what errors occur when compiling existing vision transformers. Figure 11 is an error message that appears when patch embedding and self-attention are present. An error appears that model interpretation is not possible due to an internal error. Figure 12 shows an error message that appears when a GELU is included. The error message indicates that the GELU on the TF light is not supported, and if the vision transformer model's fully connected contains bias, the following message is output and cannot be compiled, and in that error message, B shape appears to represent the shape of the bias, and M and N appear to represent the input M by N. Therefore, when the batch dimension is deleted and the patch dimension is set to the batch dimension, M is 197 and N is 176, the error appears to occur because nothing matches the first value of bias shape, which is 1. Thank you for listening, and if you have any questions, please leave a comment.